Hello. Today I'm going to be explaining Einstein's theory of relativity. So let's suppose we have a car here. It's not going to be good. Doesn't matter. Boom. Okay. Then we have one person here and one person here. Let's say the car is moving at 50. What the heck? Okay, 50 kilometers an hour. And for some reason, this guy in here is throwing a baseball or something to another guy in the other side. And the baseball is going at, say, like 5 kilometers. What did I just? Okay, kilometers an hour. That, and then there's also someone out here, someone right here, who is watching, and he sees the baseball moving at 5 kilometers an hour, but it's in the car, so he would think the baseball is moving at 55 kilometers an hour. But for the people in the car, they would be thinking the baseball is moving 5 kilometers an hour. Because they feel like they're moving 0 kilometers an hour. But he thinks they are moving 50 kilometers an hour. So let's erase all this. And let's suppose this is just gonna be okay. Let's suppose we have 2 mirrors, right like that. One up here like this, and then a laser in it. Laser would be going and then back down, like that. But up here, let's say this was moving, it would be like this. And then the mirrors would be move over, and it would keep on going like this. But, and let's say, okay, let's start over. So, mirrors. This distance right here is, I don't know, doesn't really matter. But it takes the laser 1 second to get from the top to the bottom or the bottom to the top. So, let's say the laser's like here. Bing, it's hit the top, 1 second. Goes back down, another second. But what's up here in the moving one, it would go up, 1 second. Have you noticed the problem here? Up, down, 1 second. Diagonal lines, even if they're the same, like if you measure, let's say we have a line here, a diagonal line to the same height as the vertical line, diagonal is longer. And if it takes 1 second for the diagonal line to hit the top, and it's the same amount of time for the vertical line, meaning the diagonal line is okay, let's go back and get rid of all this stuff. Meaning the diagonal line, let's have clock. So this is the clock for the vertical line. This is the clock for that. I'm just gonna have tick, 4 ticks on this. So on here, actually no, let's not use clocks. We'll use something else. Okay. We'll use just time. Okay, so let's say they both started at 1 p.m. And then, so then the vertical clock might make it, this would make the same, so, this means because it's moving a longer distance in this, not the same amount of time, but a longer distance, well, yeah, in the same amount of time for its perspective, but because, getting confused here. Okay, so it's basically like this, the vertical might be traveling for an hour, but for the diagonal to move a farther distance must mean the time is, meaning the vertical time is going faster. Or reality, the diagonal one is going slower. This is confusing, so if you don't understand, it makes sense. But so it's this time, they could make it at the same distance in maybe 123, let's say, and 125. The vertical took longer to make the same distance. Okay, that's not a good example, actually. Okay, let's get rid of this. We're doing clocks then. So here we have one clock, another clock. That's terribly drawn. Okay, you understand that. Clock. We don't even need to do ticks. Okay, so this clock up here. Let's draw these over here. Something real quick. Clock here, here, laser here, here. I'm gonna expand this one because it's gonna be the diagonal. It's gonna move. This one's not gonna move. So we have this clock and this clock. We're gonna draw 3 clocks. Okay. So because for the laser beam, it feels like 1 second. It's the same speed, but they both feel 1 second, but one's traveling the most, and they're going the same speed. So that means the diagonal one is this, vertical is like this, and meaning the diagonal speed would be slower than the other. So we can take this another way. Someone goes on a spaceship, or just, it's good. and then that goes at the speed of light, or 792 kilometers per second. I don't know how I remembered that, but I did. So let's say it's going at this speed, and then another person is just standing still, which they're not. They're not standing still. That'll be our next point. So pretend they think they're standing still. They're not actually, but we're just pretending, okay? And then, so they're going at the speed of light. Let's say this person returns in the year for them. So they return back to Earth, and then they get out of the spaceship, they walk out, the door opens, they come out, and then they meet the other person. And they were 10, let's say, when they went on it. They would be 11, because it's a year past. And then this person might be an old grandpa or grandma, because, as we said last time, it goes slower at speed of light. It's confusing to me. It took me a while to figure it out. So, our next point, as I was saying, how you can't really stand still. Well, should we go? I'm going to go back to the car scenario. Okay, I even failed even more this time. Actually, let's do a truck then. Truck will be better. Demonstration. Let's do lines here. I draw a line like it. Amazing. So someone's standing out here. Okay, I'm redoing that. That's terrible. Okay, someone's standing out here. Two people in the back here. Why did I draw lines? So, the baseball thrown to this person at 10 miles an hour, 10 kilometers an hour. Truck's moving at 50 kilometers. For this person, it's going to look like 60 kilometers per hour. But because the planet Earth is always moving pretty quickly, he may feel like he's standing still, but he's moving at a fast speed, a really fast speed. And then he thinks the baseball's moving at 60 kilometers an hour. But for these people, it looks 10 because they're in the truck, but it doesn't feel like they're moving 50 kilometers an hour. But they are. So you're sitting in a car, on a daily basis. You don't feel like you're moving, but you are moving at not the car's rate, because the Earth is moving really fast. It's impossible to stand still, because you think you're standing still. You don't feel any movement, but the Earth's moving so quick. And then one reason for this is it's normal to be moving at insane speeds, the speed of the Earth, so your body doesn't feel, and it's normal for you. And that's what we're going to cover. Any questions?